Okay, great. Wait, I have to get on this also. Okay, okay, okay. So let me see. Okay, so yeah, let me think how do I explain this in the way he's done it? Yeah, okay. Um, okay. Give me 1 second. Save content. See, let me find the right way to kind of see. So, he says indistinguishable. I agree. Yeah. Okay. So let me try. Let me maybe tell you this way. See, the idea is the following. So I will first. Yeah, I will first state it in terms of classical, and then I will go to the quantum. See, in the packing lemma, right? What we were doing, so we had this entire typical set of X. We kind of subsampled in this typical set, and when I input this, this cross guy, my distribution would concentrate in one ball. It would almost not go outside that. It would just not go outside that if I chose the red point. So so if somebody simply looked at the outcome, okay, so let me go one more step. So if I choose the blue point, then my distribution just concentrated on this. Okay. Now what is happening is the following. Suppose I don't look at X at all. I don't look at X at all. Okay, I don't look at X at all. Okay, I kind of mask completely completely mask X, and you wake up today and you are told a Y. Okay, that Y has come from choosing these red point or blue point or purple point on the in the X space. So what somebody is doing, before you sleep, somebody is choosing this point, putting it in this p x y given X channel, and tomorrow when you wake up, you're seeing the Y. You can tell exactly which point was chosen previous night, correct?
Yeah.
So the distribution of Y is retaining the information content of where it came from, right? Your Y is retaining information about, so these are distinguishable blobs, okay? Now let's go to the covering lemma. What is the covering lemma? As I wrote today, right? What is the covering lemma telling you? It is telling you the following: 1 by m summation p y given x of yn given xn of little m equal to 1 through capital M. So what is happening? I first choose the index, and once I choose the index, I put it in the black box, and the black box will pull out a y minus pyn of yn. When I sum over all yn, this total variation is very small. Do you agree with this equation on the bottom?
Yeah.
So see what you are doing. So you have the Y register here. Okay. In the previous case, there is an X register and there is a Y register. So there is an XN register and there is a YN register. In the XN register, you would either put the blue guy, or you would put the red guy, or you would put the purple guy. And out comes a Y, and based on the Y, you can tell which guy was put on the XN. Look at this process. What is this process? This process also has an XN register and it has a YN register. In this process, what you are doing, you are picking from these XN1 to XNM, right? They're also blue, purple, red, because they're also, in some sense, points coming from this typical set. So you put the blue guy, you put the red guy, or you put the red guy, or you put the purple guy, and then you're sending it through the py given x channel, right? And you get the y from y here. Are you able to say which point you put into this x register looking at the y?
Like in the earlier case, like we could do, right? Because
Because the distribution concentrated, right?
yeah.
When you come here, what is happening in the distribution? The distribution has become uniform on, see, this is very important, okay? It's very important for you to understand. This is the typical set of y. It's only the typical set of y. Yn is all over this place, okay? But I'm writing only the typical set of y. The distribution on the typical set is something like this. So it's like really like this. So how do I write this? So it's kind of, if I write, okay, I write it like this. The distribution is like this. This is the distribution. So it's 2 power minus n h of y given x at every point in the yellow region, and it is 0 outside that. Do you agree?
Yeah.
This is the distribution. In the second case, what is the distribution? In the second case, the distribution is, okay, so I'm going to copy paste. Hold on. In the second case, the distribution is completely uniform. Do you agree? On the typical set.
Yeah.
You see this? It's very important. So if you are simply, you are not seeing what X is happening, suppose that guy is operating in the packing lemma regime, then you will never see these points appear. You will never see these points appear. And you will always see in these yellow regions, and you can tell from the yellow region, okay, which point that guy put it. Okay. If he's operating in the covering regime, covering lemma regime, then you're getting all the typical sets uniformly at random. Though that guy is not putting uniformly, that guy is not putting the xn sequences. He is putting uniformly the point. See, even in the covering lemma case also, remember, even in the covering lemma, these different color points are picked uniformly at random. They are picked uniformly at random. They are not the entire typical set. Only some of them are picked uniformly at random. Even in the covering lemma here, they are picked uniformly at random. Look at this. They are picked uniformly at random. In the first case, you can tell which point it is. In the second case, you are unable to tell which point it is. You see?
Yeah.
That's exactly what's happening. The moment you take a little bit more number of points, you are gone. You cannot tell which one it is. And so this, if you look at the blue distribution, right? If you look at the blue distribution, it looks as though nature is just pulling y. It's just as though nature is pulling y according to py and giving it to you. Though that is not what is happening. What is happening is you are picking only some points from your typical set uniformly at random and you're throwing them. If nature was giving you this, it would have picked the xn and the yn according to pxy. So every point in the typical set of x would have been chosen uniformly at random. You're not doing that. You're choosing an exponentially smaller set and you're passing it through the box. But it appears as though nature is just picking from the original distribution. So it's now you've lost the information of which xn was put. They're now indistinguishable. But in the previous case, they are distinguishable. That's really what Wild is saying.
Yeah.
Sorry, just one question.
Yeah.
So you had given that.
Does it? I mean, does it make?
Yeah. Yeah. I understood. Like, why would someone want the states to be indistinguishable?
You will now see it in the quantum covering lemma. You will also see it if you also see it from this problem. If you see it in the classical also, you will see. I'll tell you why. Okay, now I'll tell you why. So let's go to this problem that I told you. See, what is the goal here? So Alice will send something to Bob, and Bob will pull out a yn, right?
Yeah.
You look at if from Bob. If you look at what Alice has generated, it will look according to px. See, so this yn, right, will come something out of the xn that Alice sees, right? Alice will see x and she will send something out and Bob will pull out a y. So that y will be a function of x. So you will guess kind of x will be also a function of y. But it turns out x will have the distribution px, y will have the distribution py, and together they will have a joint distribution pxy. So you will see the covering lemma actually come here. Your question is very good. So the motivation for the covering lemma, before you see the application of it, you will wonder why you want to do this. Why do you want to simulate py? It's a good question, but I think the proof of the quantum measurement compression, and maybe I'll give a proof of this also, and then you will get you'll get an application. You want to simulate randomness. See, I'll tell you. Okay, the way you should think of it, right? Here you are okay. I'll tell you why. I'll give you some feel. So if you see this process, right, Alice is picking some xn and passing it through the channel. Remember, if Alice was only picking the purple point, right, if she was only picking the purple point, your distribution would be only in one ball and it would be zero elsewhere. Okay. So you are somehow not rich in your randomness. Okay. So think of the y that you see, you will use it as for some cryptography or for some cipher or something of that sort. Your y is not rich enough. It is only locally random. It's random in a small set, but it's not really rich enough. You want to somehow simulate huge amount of randomness, either for cryptography or for some ciphertext or something of that sort. But that randomness can't come from nature, right? I mean, you have to do some process. Some process has to generate that randomness. When you generate that randomness from that process, this randomness will be kind of linked to that source. Now, what you are doing here is that you are completely delinking yourself from the source. So, though Alice is pulling out xn of 1 today, xn of 2 today, xn of 3 today, you look at y and you have no relationship with that, what she has pulled. So in some sense, you're generating randomness that is really, uncoupled with its source. And that is useful many times in cryptography. I mean, I can give you this kind of a thing, but you'll see a further application.
Okay. Yeah.
Because see, if you go here, right, if you're working in the packing lemma regime, then your yn has still memory about the xn. So somebody could possibly utilize that. You don't want to use such a kind of a secret key possibly.
Yeah, right.
See, no randomness. See, people have, by the way, in computer science, in theoretical computer science, there is a lot of speculation whether you can actually generate pure randomness. Even the randomness that you generate on any MATLAB or anything, right? It is coming from some key. It's coming from some process. It's not purely random. Okay, somebody can actually regenerate that randomness. So it's not really random, and it is of a lot of interest as to how to generate randomness. So here you're getting like pure randomness starting from a deterministic process. This is a deterministic process. You pass it through. Okay, the question is, is this black box? Can I simulate this black box? That's a question I will kind of not deal with. But essentially, you're kind of decoupling your randomness from some source.
Yeah. Okay.
Information theory is very deep. It's very hard to. Information theory has too many. I mean, actually, this is like people won't do even the classical covering lemma in a first course in information theory. So it's kind of anyway long. Okay. Is done?
Yes, sir. Yeah.
Okay. Teachers, you
Okay.
can go ahead.
Thank you, sir.
Sure. You can stay. I mean, I just don't want somebody to wait without. Yeah. Tejas, yeah.
Oh yeah, so I'll just share the screen.
Yeah. Hold on. Let me stop recording, right?
Yeah. Oh, sorry, just one question before I share the screen.
Yeah.
So in this case, like the classical covering lemma, not
Yeah.
classical covering lemma, you asked for that protocol which Bob has to reconstruct, like Bob has to put some Y in his register so that the joint thing is PXY, right?
Yeah, correct. This problem.
Yeah. So if Alice just send, so you take this set, which is given by this classical covering lemma,
Yeah.
like this capital M sized set,
Correct.
and Alice just sends those strings, then by this result, Bob would end up simulating. So basically, Alice is sending this xn of small m of this. So there'll be capital M, many of them, right? So then, as per this thing which you have written here,
No,
this
but
summation of
no, you got the premise wrong. That's why I'll interrupt. See, Alice can't. The X is coming from nature.
yeah, correct.
She has to do something on that X. I mean, she can't do, but she has to send something to Bob so that Bob can pull out a Y, so that the X and Y will look as though it came out of PXY.
Yeah. So, I mean, yeah. So, like, if she gets like n copies so far, right? Let's say she has got n instantiations of this random variable.
Correct.
Px.
Correct.
So then she doesn't basically look at them. She looks at this capital M size set, which is there.
Okay.
Like for that small n, you have some capital N size set, like this set exactly.
Yeah. Okay.
Xn of small m.
Yeah, but see, she would have got somewhere in this typical set. She would have got somewhere in this typical set. So she has, okay, give me 1 minute. Let me color the points. So there's a green dot, and then there is another green dot, there is a purple dot, there is a blue dot. All these dots are there.
Yeah.
These are your, you can either, if you take a little more, they cover. If you take a little less, they pack.
Yeah.
Now she has got a point. She's got some point here. What will she do? She's got the crossed point. Nature has given her the crossed point because nature is picking uniformly from the typical set.
Yeah, correct. Yeah, but if she sends more than 2 raised to n I xy plus some delta. overall,
Yeah.
then she will simulate this covering lemma kind of situation, and then
Correct.
the total variation distance would be less than eta.
Correct. No, that is true.
Oh, no.
Total
Sorry.
variation distance
Then the-
of Y's distribution.
Of y, correct. Yeah, we want p of xy, not p of y.
Yeah.
Okay. This is just close to Bob's marginal, which is p of
Correct.
y, not
Correct.
p of x.
Correct.
Oh,
correct.
correct.
Exactly. You're able to simulate Bob's marginal.
Which even he can do.
But because you're operating the covering lemma regime, the point, I mean, the relationship between the x and y is kind of broken.
Yeah, correct.
I mean,
like they just cover the whole space.
Yeah. Think of it. So I'll give you a clue. Think of it other way around. Think of as though Bob is trying to cover Alice's space. Get some thought that direction. See, because what Alice is seeing X. So now somehow Bob has to pull something out so that X and Y. Yeah, I know this is slightly tricky. This is not an easy problem. By the way, this was solved only in. This was solved actually. This has an interesting connection even with computer science. So it was solved in some sense jointly, not jointly. I would say concurrently by two people, two teams. One was a TIFR. It is a nice paper, a bunch of authors, and one was I think this was 2014 or something, 13, 14, 15 or something. This was by Paul Cuff. And yeah, it's a nice thing. So my clue to you is look the other way. Look the other way, and I would suggest you to look at the bipartite graph of the typical set that I talked about last class. What is, see, I told you one thing, nature is picking the edges uniformly at random. So somehow you have to simulate that.
Yeah, correct.
You are seeing only one side. How do you, what do you ask Bob, which dot do you ask Bob to put his hand on, so that the hand that he puts, the point on which he puts his hand and the point that Alice sees, that edge, that distribution is becoming uniform on this graph, right? If you can somehow simulate that, then you're in good shape.
Yeah, correct. If you simulate the joint typical set of xy,
yes, correct,
then you would simulate p of xy.
Correct. And go back and look. Okay, so I can't resist myself giving you this clue. So think what happens when nature picks an X, right? If nature herself was picking the Y, what would she do? She'll pick an X, she'll sit with that X. How will the Y look?
It will look jointly typical. I mean conditional typical with respect to that X.
Yeah, it will be uniform in that conditional typical set, right?
Yeah.
So if you are in that, so if Bob pulls out uniformly from that conditional typical set, then we are in good shape. Then we are pretty much done, because that's what nature is doing.
Yeah, correct. Yeah.
So somehow he needs to get to know which conditional typical set he has to pick from.
Oh, okay.
So think in that direction. It's a very beautiful solution. It's a very beautiful solution. And your understanding of this classical solution will give you a very good sense of your understanding for the quantum thing also.
Okay.
Yeah. Okay. You wanted to share screen, right?
Yeah.
Okay, give me 1 second. No, hold on.
Quick question.
Hold on.